So last time we talked about modulation bandwidth of LED. Now by modulation bandwidth, what we mean is how fast can we turn the LED on and off. And we said that is directly related to how fast can you, that's directly related to how fast can you change your carrier density. Okay. So we had derived an expression for the injected carrier density per unit volume in the presence of modulation, and the h of j omega, the transfer function in the presence of modulation, we derived, and we figured that the modulus of the transfer function is given by 1 by square root omega m square tau c square, where your tau c is your effective recombination time, which includes both radiative and non-radiative recombination. Omega m is your modulation frequency. Now the question we are asking ourselves is, what is the modulation bandwidth? So that's a frequency at which the transfer function drops to half, full, if you were to do it full width at half maximum. Of course, we recognize that this is similar to that of the transfer functions is similar to that of a low pass filter. So you can allow low frequencies, you can have modulation at low frequencies, but as your frequency starts going higher, fundamentally physically what happens, the carrier is not able to respond to that frequency. The carrier recombination takes some time. If my input changes faster than that, the carrier is not able to recombine and create a electron hole pair and recombine at the same rate as I am changing my injection current. So the frequency at which this goes to half, we derived last time, it is root 3 divided by 2 pi tau c, where tau c is, I will remind you, is the effective carrier lifetime, and remember this has contributions from radiative and non-radiative lifetimes. Did not discuss last time is electrical bandwidth. So what is this idea of optical bandwidth and electrical bandwidth? The transfer function we derived is the ratio of the carrier density due to the injection current at a frequency omega to the carrier density for 0 frequency. Now carrier density is proportional to the number of photons, because we say each electron hole pair, a fraction of the number of electron hole pair combinations give rise to a certain number of photons. So this is proportional to optical power. So this h of j omega that we have written, I can also write it as a ratio of P optical at omega divided by P optical at 0 frequency, right? And that magnitude of that is 1 by square root of 1 plus omega m square tau c square. However, so this is the speed with which your light will respond. However, if we ask ourselves a question, what is the corresponding driver, electrical driver bandwidth, which will give us this optical bandwidth? In other words, let us ask ourselves this question: given a certain f3 dB optical, and f3 dB optical is decided by the fundamental carrier generation mechanism, the electron hole recombination, right? Given a certain 3 dB optical bandwidth for an LED, what should be the bandwidth of the driver electronics that can support this f3 dB optical? Okay. So how do I drive an LED? When you say driver electronics, what do you actually mean? To operate an LED, this is the circuit symbol of an LED. It's just a PN junction which is light emitting. So under DC conditions, you would forward bias this. There could be some biasing resistor. So this is how you would bias a LED. But how would you now add an AC onto it? Instead of DC, this has to be replaced by your AC, right? And this AC has to have not, so this AC that you are using to drive is not biased, it need not be biased at 0, or in other words, if I draw the Li characteristics of the LED, this is the light output, so it is also called as PI characteristics or Li characteristics, light output versus current input. It is a straight line passing through the origin, and we discussed last time that the characteristic feature of the LED is that the Li characteristics is a straight line passing through the origin. Now, if I am giving a modulation, I could bias this at, let us say, at this point, and about that I can give a current which is changing as a function of time. So this axis is my time axis, here is my current axis. It goes from, let us say, IB to Imax to Imin. So this is my IB, and I could go from IM, and this is current as a function of time. You could do this, typically this is done using what is called as a bias controller circuit, or rather a bias T, where you will have the AC that you want to modulate pass through a coupling capacitance, and a DC, which is your bias current, whatever is the bias current you want to decide, that pass through inductance, and the combination of this is what would drive the LED. Even for a laser diode, this is how a typical biasing circuit will look like. This is the AC signal that you want to convert from electrical to optical input, and this part is called as a bias T circuit. So the DC part of the AC signal is stopped by this coupling capacitor, and you have just the DC part pass through the inductor, and that would drive your LED, or it would drive the laser diode. Okay. The question we are asking is, what should be the bandwidth of this circuit, right? What should be the bandwidth of this driver circuit, so that it can support a specific 3 dB optical. So what do you think the answer should be? Is it the same as F3 dB optical? It should be larger than F3 dB optical, or can it be smaller than F3 dB optical? What is your guess? Okay. Let us take an example. Let us say tau c is some 50 nanoseconds. Okay. Now, let us calculate what is 3 dB optical. From what we derived earlier, this 3 dB optical has to be √3 times 2 pi tau c. Can you calculate what this number is? .5 megahertz. Okay. So the basic construction of this LED tells us that you can modulate it only as fast as 5.5 megahertz, because the recombination time is 50 nanoseconds. Okay. But now the question is, what should be the bandwidth of the drive circuit? Should it be 5.5 megahertz? Should it be something smaller than 5.5 megahertz, or should it be larger than 5.5 megahertz? What does your intuition say? Should be at least 5.5 megahertz? Is that what you feel? What is the relation between the current and the optical power? you see this drive current is your optical power. Here we have the graph. The optical power is proportional to the drive current. This is electrical drive current. Okay. So, if you talk about 3 dB bandwidth in an electrical circuit, how is 3 dB bandwidth of an electrical circuit defined? So, you say electrical 3 dB bandwidth, you can find out electrical 3 dB bandwidth by using this ratio P electrical omega divided by P electrical 0 frequency. Okay? You should be able to find it out from the electrical transfer function. Now, how is this electrical transfer function related to optical transfer function now? This electrical power is proportional to P electrical. Electrical power consumed should be proportional to current. Is it proportional to current? Electrical power is proportional to current square. It is not proportional to current. Correct? So, and my optical power is proportional to current. So, what should be my electrical transfer function? It should be proportional to, I know my optical transfer function h of j omega is 1 over square root of 1 plus omega square tau c square. And this is optical transfer function. Now, optical transfer function is a relation between optical power at omega frequency to optical power at 0 frequency. Now, optical power is proportional to current, and we want the electrical power ratio. So, electrical power is proportional to the square of the current. So, which means the transfer function must be equal to square of this. So, this must be equal to 1 by 1 plus omega square tau c square. And this is an interesting relation, and from this, what would be the 3 dB bandwidth? F 3 dB electrical would be equal to, so that would correspond to the case where this transfer function falls to half, and that would be given by 1 divided by 2 pi tau c. In other words, P electrical omega divided by P electrical 0 is actually 1 by square of the corresponding optical transfer function. So, this is 1 plus omega square tau c square. Therefore, F 3 dB electrical is the frequency at which 1 plus omega square tau c square, so this is 3 dB, is equal to 2. So, omega square tau c square is equal to 1. So, frequency 3 dB electrical is 1 divided by 2 pi tau c, because we know omega is 2 pi f. So, what is the relation between optical bandwidth and electrical bandwidth now? So, f 3 dB optical is actually root 3 times f 3 dB electrical. So, for the previous question, tau c was 50 nanosecond. You calculated f 3 dB electrical to be 5.5 megahertz, right? You calculated its 5 optical, yes. You calculated optical to be 5.5 megahertz. So, this is slightly counterintuitive, that you don't need 5.5 megahertz. Your drive circuit need to support only 5.5 megahertz divided by root 3, which is approximately 3.2 megahertz. You need to have a bandwidth of only 3.2 megahertz, all right. But when you are actually carrying out an experiment to measure this bandwidth, you have to consider multiple things. Let's say you are trying to run an experiment to measure the electrical bandwidth, to measure the bandwidth of an LED. What bandwidth are you finally concerned with? Are you concerned with electrical bandwidth or are you concerned with optical bandwidth? So if you are building a driver circuit for LED, you have to worry about electrical bandwidth. Let's say you have an LED, a driver circuit that drives the LED. So you are worried about 3 dB electrical. But you know that if I have a specific 3 dB electrical, optically it is anyway √3 times more than that. You will have to worry about it only if it were less than the electrical bandwidth, but this is anyway more, which means that my light that is coming out on and off will respond to definitely what I give at the input of my driver circuit. But when you are making a measurement, how do you make a measurement from the output of an LED? You would connect a photodiode at the output of LED. Okay. Now, if you were to measure the LED bandwidth, what should I also take care? I should also take care that my bandwidth of the photodiode that I am using to measure the LED, measure the bandwidth of the LED is more than the LED bandwidth itself, so that I can measure that bandwidth. Okay. So, in a measurement, what also comes into play is the PD bandwidth, and which we will talk about when we talk about photodiodes. Okay. So, in a whole measurement system, we have to also worry about the photodiode bandwidth. Now, what we have also not considered here is parasitics. So, this is one idea you need to consider before you measure when you are trying to measure the LED bandwidth. The other factor that you need to consider when you are measuring the LED bandwidth is parasitics. Let us say you are using a cable which has a large capacitance, and that it is like a transmission line which now limits the bandwidth of operation of the LED. That is something you need to consider. So, for example, in this bias controller circuit, you cannot afford to use cables, for instance, here or the cable that connects to the LED in such a way that the cable is now imposing a bandwidth limitation. The capacitance of the cable is larger when compared to this. That also will be a problem. The other parasite, so the one parasitic you need to consider is about the cables. The other parasitic you need to consider is, your LED is a PN junction. Now, PN junction comes with certain junction capacitance, right. So, you are not worried about that in the junction capacitance. The reason why you are not talking about that here is because when you forward bias the LED and when the LED is heavily forward biased, the junction capacitance actually comes down, right. So, when you are trying to make an LED by improving its tau C, the fundamental limit may come from the parasitic capacitance from the junction. So, cables, junction capacitance, etc. are not considered here, because when we just say 1 by √3 divided by 2 pi tau C, we are only considering the fundamental limitations because of the recombination time. But typically that number itself is so small, the bandwidth, it is only 5.5 megahertz. So, typically the cable capacitance, if you use a decent enough BNC cable, that is not actually the limitation. The limitation typically comes from tau C itself, which is why you are not considering all this. Okay. So, that completes the electrical part, the modulation bandwidth part of the LED.